In this video, we shall use MATLAB's MeshGrid and Quiver commands to draw some vector fields for first-order ordinary differential equations. So let's suppose that we have a first-order equation, typical form, y prime equal f of ty. And suppose we're in a situation where none of our symbolic methods apply. So we will utilize what's sometimes called a geometric or graphical method to get a global idea of the nature of the solution curves. We should also presume that the standard existence and uniqueness theorem applies. So both f and its partial derivative with respect to the variable y are continuous functions on some rectangle in the ty plane. We know in those cases that there is a set of non-intersecting curves throughout R that are the solution curves to the ODE. We have no formulas for them, but we can approximate them graphically using MATLAB's, as I said, MeshGrid and Quiver commands. Okay, so how does that go? Let's suppose we take a point, t0, y0, in the rectangle. We know there's a unique solution curve through that point, which goes through the point and solves the differential equation. We don't have a formula for it, but we know it exists. So y equals phi of t. It satisfies the initial condition, phi of t0 equals y0, and it satisfies the differential equation. Phi prime of t is equal to f of t phi of t, and this will be true for all points t in some interval containing the point t0. The whole story of how big the interval is something we've talked about, and it's a somewhat sophisticated idea. We'll come back to that at another time. Okay, as I said, we don't have a formula for phi, but we can use f to actually do something rather geometric. We can take a point, again, t0, y0. We don't know the formula for phi, the solution curve that runs through that point, but we do know the value of its slope. That is, since phi prime of t0 must be equal to f of t y0, t0, y0, then all we have to do is evaluate the given function f at that point, and that will give us the slope of the solution curve. So we select a matrix of values spread throughout the region R. We evaluate f at those points, and then we draw a small slope segment at each of the points with slope equal to the value of f at the point. This is called a vector field. For the differential equation, or the ODE. It gives a general indication of the nature of the solution curves of the ODE. So if we're here in our rectangle R, let's say, and we've specified some point, t0, y0, we know there's a solution curve that runs through that point. We don't have a formula for it, but we do know what its slope is. Slope of the curve through that point. So we use MATLAB to draw lots of slopes, little slope segments throughout the region R, and it will give us a general indication of the nature of the solution curves. So we will now illustrate by drawing 3 examples freehand, and then we'll draw much more precise vector fields using MATLAB's commands. Here is example 1. So example 1, y prime equals y squared. So we're going to draw the vector field for that. Before doing that, here's a remark that if you have an ODE and you want to draw its vector field, the slickest way to do it freehand is to consider the level curves of f. So if you look at the level curves, and then for fixed c, the slope vectors will all be the same, and sometimes by employing that technique you can have a successful drawing of the vector field by hand. So in particular, let's look at the cases y squared equals c. And we'll just look at 2, c equal 1 and 4. Actually, also 0. Okay, so for 0, y squared equals 0. That amounts to y equals 0. And along the curve, the slopes are all 0. Next, look at c equal 1. Y squared equals 1 when y equals plus or minus 1. And so along those two lines, the slope will be 1. So along y equal 1, the slopes of the solution curves are all 1. And similarly, along y equal minus 1. And also for c equal 4, y squared is 4, y is plus or minus 2. So along those two lines, the slopes are all 4. So much steeper. Not so great freehand, huh? Okay, so there's your vector field, and you could try to fit in some curves. Well, it looks something like maybe this might work. And of course, y equals 0 will be a solution curve. And you wonder, well, is that possible? It's conceivable you have a solution curve something like this where it crosses. But in fact, that's not the case, because one can actually solve this differential equation rather easily. It's separable, and if you do, you see that the solutions are of the form 1 over c minus t. So they're all hyperbole with vertical asymptotes. In a moment, we'll employ MATLAB to verify these facts. Now for example 2. Y prime equal y plus t. Not autonomous anymore, but we can still employ the same technique. Look at the level curves of y plus t. When y plus t equals 0, that's a 45-degree line going from the second to the fourth quadrant, and the slopes along that line will be 0. Next, we look, say, at y plus t equal 1. That will be a line parallel to the original line, but 1 unit up, so we're going to have something like this. And similarly with y plus t equal 2, steeper. Y plus t equal minus 1 is the line, 45-degree line, 1 unit down from y plus t equals 0. And when y plus t equal minus 1, the slope is minus 1, and so we just get that line. And similarly, when y plus t is minus 2, we get something like that. So, there's your vector field. What do the curves look like? Maybe something like this. And of course, this line is a solution curve. Now again, this is a linear equation and rather easy to solve. And if you solve it, you get y equals c e to the t minus 1 minus t. So look, there are the curves. Notice for the special case that c equals 0, we get the solution y equal minus 1 minus t, and that's the straight line depicted here. Now for our third and final example, let's look at y prime equal t squared plus y squared. That's a nasty little equation. In fact, it's not possible to solve that algebraically. There's no formula solution for that. But we can still attempt to draw the vector field. What are the level curves on the right-hand side? Obviously, circles, right? When t squared plus y squared equals 0, we just get this point here with the slope 0. When t squared plus y squared equal 1, we get the circle of radius 1. So around that circle, all the slopes are 1. Around the circle of radius 2, we get steeper slopes. And steeper as we go further out. So there's your vector field. Not too illuminating, But one could attempt to draw some solution curves, and it looks like you have something like this, maybe. And it will turn out, as we'll see later on when we do a numerical solution, that that's not such a bad approximation, and we'll also use MATLAB to draw the vector field itself. So now let's turn to MATLAB to actually do these three examples. Okay, now we're going to turn MATLAB loose on these three problems. Here's the first problem, y prime equal y squared. We first set up a grid, a rectangular grid, where t runs from -2 to 2 and step size 0.2. Y runs from -3 to 3, step size 1/2. S is the right-hand side of the differential equation, y squared. Let me skip L for a moment. Then Quiver says, draw a bunch of vectors at the points of that grid with a length, if you ignore the L for the minute, coordinates 1s, which is, of course, a little vector with slope s. And then we divide by the length of the vector. That's what the L is, to ensure that all the vectors we draw have the same slope. And here's a scale factor, which, to quote the MATLAB book, reduces the length of the vectors by 1/3 roughly, to prevent the arrowheads from swallowing up the tails of nearby vectors. We labeled the x and y axes, the t and y axes, and we titled the graph. Axis tight, also to quote the MATLAB book, automatically sets the ranges to include the entire graph. So let's evaluate that. And there's our vector field, very similar to what I drew by hand. As I say here, recall that the solution curves are y equal 1 over c minus t. That's clearly evident from the vector field, at least in terms of the general nature or the general shape. Okay, so that's our first example. Let's now look at the second example. Y prime equal y plus t. I set up a similar mesh grid, this time from -3 to 2. S is y plus t, the right-hand side of the differential equation, and after that, the directions are exactly the same, except the title, of course, is a little different. Let's evaluate. And there's the vector field. Looks very similar to the picture we drew, except it's a little hard to pick out the straight line solution over here. So recall that the solution curves are c to the t minus 1 minus t, and those are evident from the vector field. But as I say, perhaps the straight line corresponding to the case c equals 0 is not so clear, so let's add it. So I set hold on, which means draw on top of the previous graph, and I use just the plot command to plot -1 minus t, run the section, and so I need to go find the graph. There it is, and there's the straight line solution. So there's a direction field for y prime equal y plus t. And finally, let's look at the third example. Y prime equal t squared plus y squared. This is one that we can't find a formula solution for, but the method is exactly the same. We set up the mesh grid, right-hand side of the differential equation, normalized by dividing by the length, and title it appropriately. It says here, recall that we cannot find a formula solution for this ODE. Later on, we'll find a numerical solution, and we'll compare with the graph depicted. Let's see what the graph is. There it is. So there's your solution. There's your vector field. Some solutions going like that, maybe like this, like that. And so one summarizes with the following. For the record, it looks like the solution curves increase monotonically from -infinity to infinity, and that for these curves, for those curves that pass near the origin, the curves flatten out for a while for those that are far from the origin, the increase is rather steady and quick. What is not clear is whether the curves go to infinity in finite time or not. That is, whether there are vertical asymptotes. So again, let's bring up the graph So are these blowing up in finite time, or are they going off to infinity in infinite time? In fact, when we do the numerical solution, we'll see that they blow up in finite time. A quick addendum, when I was doing exercise 1, I misspoke. I said we divide by L to ensure that all the vectors have the same slope. I, of course, meant that we divide by L to ensure that all the vectors have the same length.